Okay, thank you very much. So, hello everyone. My name is Alexandre Neto. How are you? I am fantastic and I'm doing really well. I will now present to you my study on the numerical evaluation of damage in laminated composite tubes under low speed impacts. Starting with the index, I will first give you a topic overview, then we will move on to the research motivation and objectives to then introduce the literature review. I will mainly focus on the methodology and especially the results and findings, ending with the main conclusions and the ongoing work. So to contextualize this topic a bit, I believe you all know that composites are very common nowadays, but they can also be very fragile under certain situations where common damages such as delamination, fiber and or matrix cracking can occur, especially under impacts. Impacts such as low velocity, which are very common in service conditions, can cause consequences that are often overlooked due to not being visible to the naked eye. To combat that, there is a need to study energy variations and determine a gradient to better understand such loads. So, what motivated me to perform this study? Good question. I wanted to ensure advancements in the correct dimensioning of carbon fiber reinforced polymer structures, have a great contribution to the understanding the effects of low speed impacts, and especially to make composites last longer and be stronger. Objectively, I wanted to perform a numerical evaluation of composite tubes under low speed impacts by promoting various impacts with different energy levels to correlate with the strain results that we'll see later. For the specific layups I will study, I will define the energy limit that produces residual damage, and in future work, I will create a parallelism between residual strength and fatigue life in experimental testing. Okay, so as for what other authors have done, one of the differences in my work is that I will use a vertical drop weight test apparatus instead of a drop hammer test, as you can see in figure 2 here, used by author number 1. Other important conclusions by authors are listed here on the right, but I will be mainly focusing on the following. First, the fact that quasi-isotropic laminates offer better resistance to impacts. Second, the lamination resistance is influenced by the tube layup and does not develop between plies with the same orientation. Third, and that certain layups are more appropriate for distinct loads and load types. Well, we will see by the end of the presentation if I've achieved the same results. But before going to the methodology, I highlighted 3 main points that I found other studies were missing. First, assessing the effects of invisible induced damage on the tube life cycle. This will occur in future work. Second, finding energy limits that produce residual deformation on different layups. And then third, obtain a classification of the structural integrity of a composite tube under gradient low speed impact tests. Now, about the methodology. We start with the Alexandre parameters, which is the software that I use, Alexandre, where I use 2 types of mesh elements due to the geometry and the thickness of some. For the impactor, I used MAT 001 elastic, and for the supports, I used 024. And to model the composite, I used MAT 54, option 55, very important, due to the Tsai-Wu-Feili criteria that were preferred. And the consistent units you can see in table 1. And I used hourglass 4 for a more realistic contact and the default element form 1. On the right, you can see the numerical test apparatus, which was based on the ASTM D7136, which is a mouthful, let's say, but instead applied to tubular profiles with the drop weight test method, securing the tube at each end. One very important detail that you can see in figure 5 is that I modeled the 12 composite layers individually so that they could be evaluated separately. This will be very important. Okay, so how did I proceed with the numerical elastine testing? Fundamentally, thanks to a trial and error approach until Tsai-Wu-Feili criteria limit was met. For this analysis, it made sense to have three different energy damage tiers. First, internal damage, where the tube suffered internal visible damage. It's self-explanatory. The second, which I called intermediate level, is acting as a midterm between both tiers to show the damage evolution. And then the third, the visible external damage tier, where there was apparent visible plastic deformation to the outermost layer. We can see in table 2 that two different layups were tested, L1 and L2, having very distinct orientations to examine potential differences. And we can see each energy value that created the damage mentioned in every tier for each layup. We can clearly see by looking at table 2 now that L1, the layup 1, was able to sustain higher energy values throughout the tests. And this is what we'll be exploring and analyzing next. Okay, so starting with the internal damage tier, where we have firstly the force times displacement graph up top for both layups, and then below the total energy, meaning kinetic plus internal, varying with time. On the center, more or less, we will have the tube behavior during impacts, and on the right, the key findings. This logic will be used to analyze the three tiers. So this tier, firstly, I want to say that the disappearing elements you may see signified surpassed criteria values, meaning that the part has permanent damage when that occurs. So we can conclude that L1, so layup 1, suffers lower peak impact force despite higher energy impact, but shows more deformation. Also that L1 displays less internal damage than L2. You can see that in the animation. That L2 has more internal damage, but less permanent plastic deformation. That L1 has higher values of total energy most of the time. And damage to L2 is only to the most inboard layer, as you can see in the animation, which is very curious, unlike L1. Moving to the intermediate damage tier, we can see that the force displacement graph curves have similar profiles despite different layups and impact energy. That L1 suffers more than double of the impact energy, but it doesn't translate to twice as much plastic deformation, which is curious. That L1's peaky FD curve near the maximum displacement is due to the energy dissipation during heavy impacts. Also, the energy times time curves behaviors are identical. And lastly, for this year, that L2 damaged fill elements are more widely spread, despite impact being despite impact energy being less than half, which is very interesting as well. Moving to the external and last external damage tier. Again, L1's peaky, let's say FD curve near the maximum displacements, is due to the two hitting the impactor after recuperating elastically. Both FD and ET curves have are similar despite massive energy differences. For me, this is mostly the most curious thing, that the outmost layer failure in L1 occurs after the rebounds, after impact, and L2 suffers after the initial contact, which is very interesting. And lastly, the L2 damaged fill elements are more widely spread despite dissimilar impact energy. Okay, so in order to correlate the impact energy level with the strain results, layup 2 was chosen in the state of external visible damage, where the most energy happens, to showcase the influences of the layer orientation on being subjected to strain in the moment of the most displacement regarding the impactor. Obviously, blue means no strain and red means maximum strain in this case. So we can see similarities between the layers with the same orientation regarding the way the strain is distributed. And most notably, the strain evolves in the opposite direction of the fibers, being the fourth layer, the -45, very apparent, as well as the outmost layer on the far right, where the orientation is 0 degrees axial and it suffers a lot transversely. Concluding, Starting with the study points that require further attention, I found that MAT55 properties massively influence the outcome of the results, not only affecting impact behavior, but failure criteria limits as well. So it is critical to insert the correct values in the MAT card. Meshing posed a significant challenge, during which I discovered that the selection and sizing of elements are pivotal, really, for achieving a reliable and reasonably accurate simulation. However, the limitation imposed by layer thinness remained a persistent obstacle to that. Also, the lamination was not a major consideration of this study, as it implied a lot more computational power, and the software was not really a friend when trying to achieve that with the cohesive elements. But the major takeaways of this study are that the tube layer can drastically affect sustained energy absorption and damage, as per author 2, that L1 displays less damage in comparable situations, unlike what author 1 said previously, that invisible damage is still damage, and that may compromise part lifespan, that there is a relation, as we've seen before, between fiber orientation and strain distribution, and its consequences will be evaluated with experimental testing, much like author 3. And then to finish, I just want to give you a heads up about the ongoing work related to this study, where numerical tests will continue for more layups, and then experimental drop weight tests will be conducted in a machine like Figure 7, where the drop height is directly related to the potential and kinetic impacts energies. Also, the MAT55 parameters will be tuned after the tube manufacturer provides accurate data, or more accurate data. And then the energy gradient will be adjusted for each layup, where I will test 3 more layups with the following orientations, and as you can see in the table 3, which is plus minus 55, plus minus 30, and 0 degrees axial. And that is all. Thank you for your attention, and feel free to ask any questions.
Thank you for your presentation. The session is open for questions. Yes. Please, the microphone to Professor Torgensen.
Thank you for a very nice presentation.
Thanks.
How was the interface between the layers modeled? Was there any friction between the layers?
So I can show you here in the table 1. You may see where I have the simulation. There's about the contact, automatic general. So I found that this contact, the automatic general, was the best for this situation after consulting the Alexandre manual and performing lots of tests. This mainly is regarding the contact between the impactor and the tube. But yes, I believe that accounts for friction between the layers as well, yes.
Okay. And adhesion as well?
Yes, it does, but it's, like I said in the conclusion, it's not the best approach. I could have used, well, I've tested that there's a function called cohesive elements, or another mat that accounts for that, but I had many problems due to my geometry and the fact that I'm using 12 individual layers. I had to create an interface between the layers and the software, or at least as of now, I do not have the knowledge to perform that. So it was not ideal in terms of simulating the delamination, but it was a very good example to get an idea of the crashworthiness of the tube in terms of energy and invisible damage.